Hello, everybody. Let's get started with lecture module 2. This is video number 1 and lecture module 2. This is going to be our first content video for this lecture module. I'm going to go ahead and bring up the slides. I have some fancy screen sharing techniques I need to do this time, so hopefully everything is going to go nice and smoothly. All right, so hopefully you can now see my screen. I'm going to make everything full screen right here. So here we are. So we're going to be talking about how we're going to move from a protoplanet, which we finished building at the end of lecture module 1. So we're going to consider, say, a terrestrial protoplanet, and how do we go from a freshly made protoplanet to a planet? And one of the first things that we're going to have to do is we're going to have to melt it so we can layer a planet according to its density. So we can end up with something like the Earth that has a iron core and then a high silicate mantle, a high density silicate mantle, and a low density silicate crust. This process of layering a planet by density is called planetary differentiation. So that's how we're going to start this video. We're going to remark that lots of things that we see in the solar system are differentiated, so there must be some process that differentiates them. And the trick is going to be to get something to layer itself by density, to get the dense stuff to sink to the center and the light stuff to float to the top. Well, if we're talking about stuff sinking and stuff floating, we need to have the protoplanet to be molten, or at least partially molten. Significantly, enough of it needs to be molten so that you can kick off this differentiation process. So we have to talk about the sources of heat to melt a protoplanet. How do you get so much heat and energy that you can melt an entire protoplanet? And the trick is going to be radioactivity. That's going to be our main factor. So we'll spend some time talking about that. All right, so we ended our story of planet building with protoplanets. And for this video and the videos that are coming up, I want you to picture proto-Earth. So we have the accretionary process. We're taking those metal and rock grains, they're getting together, clumping together, building up to larger and larger and larger objects. So eventually we enter the planetesimals. They play their game of Highlander. Then you get the proto-Earth, and it's accreting a bunch of other materials until we end up with what is going to become the Earth. Now let's think about the accretionary process. We're just taking materials and we're putting them together. It's not like we have any sort of sorting mechanism going on. We're not grabbing all the metal bits and putting them in the center, and then all the high density silicates and adding a layer of that, and the low density silicates and adding a layer of that. When we create a protoplanet through accretion, everything's going to be mixed up relatively evenly. This would be what we call homogeneously mixed. So it's all evenly mixed, but we can see, we know that the Earth has a metal core, a high density silicate mantle, and a low density silicate crust. The same is true for all the terrestrial planets and many of the large asteroids, that the planets themselves are layered by their densities. The densest stuff, the metal, is down in the core. Then as you move towards the surface, you get lower and lower and lower density. You are sorted by density. The densest is in the center, the lowest density is on the surface. This is the process that we call planetary differentiation. But how do we get it so we can move the dense materials to the center? I could take a chunk of metal and I could just plop it down on this table. Imagine that this is just the surface of the Earth. So let's just imagine I take this coffee cup right here. Set my coffee cup right down. It's a solid. It's just going to sit there. It's never going to go through the table. If this was a big metal thing, it wouldn't sink towards the center of the Earth. You can't sink a solid through other solids. So how can we actually get the dense stuff to settle in the center and the light stuff to settle on the crust? Well, what we need is we need the planet to be molten. And that is actually a tricky business, because we're just going to have everything homogeneously mixed, and now we need to layer it by density. And to do so, we need a protoplanet that's mostly, or at least partially, molten. And whenever I say partially, pretty molten. So how do we melt a protoplanet? Where are we going to get all that energy, all that heat to melt the rocks, turn rocks into lava, turn metal into liquid metal? Well, we have a variety of energy sources. And what I've done is I've tried to put the all the sources of energy that can heat up a protoplanet. And I've tried to put them in the time sequence order in which they would occur during formation. So let's start at the beginning, and I'll discuss how much energy they provide and whether or not it is sufficient to melt a protoplanet. So originally we have the solar nebula, and we're taking a bunch of materials and we are bringing them together. We are taking gravity and having gravity pull them all together into our protoplanet. So we have all the gravitational energy being squished together into a small volume, so we can convert gravitational potential energy to heat. And that's going to happen anytime that you're going to be forming something. That's how we got the temperature gradient in the solar nebula. Question is that to say something, say form a Earth via that method, take all the material of Earth, spread it out, and let it all form a Earth-sized object, we can calculate directly how much energy that is, and it's not enough to melt a planet. So we can't melt a protoplanet that way. Okay, so that didn't work, but now let's talk about the accretionary process itself. You have the proto-Earth, and early on, there's lots of planetesimals zinging around, even other protoplanets, and they're smashing into one another. And eventually, now we'll have the surface of the Earth down here. You have all these large impactors coming in, repeatedly striking the surface, depositing their kinetic energy, their energy of motion, into the surface of the proto-Earth. And there's a lot of impact. So this is a pretty efficient way of delivering energy, but it's trying to it's delivering the energy from outside and trying to get it towards the center. So this, we can estimate that this can melt the surface of the proto-Earth down to the depth of maybe a few kilometers, a few tens of kilometers. But the center of the Earth is 6,400 kilometers away. Not sufficient to melt the entire protoplanet, and we need that core region melted if we're going to sink materials, the metal, the densest stuff, down to the center of the Earth. Okay, so two ideas. Yes, they are contributing to some heat, but not enough to melt the planet. The next thing is going to happen is we have our protoplanet. We've just taken a bunch of materials and mixed them together. Not all materials are stable. Some elements are radioactive. You're familiar with such things like uranium and plutonium that are radioactive. They undergo radioactive decays. They shoot off energetic particles and energy as they go from an unstable form to a stable form of the element. And that firing off of energy, of turning from something that's radioactive and unstable to something that is stable and not radioactive, that is going to provide a source of heat. This is actually how we power a lot of our spacecrafts. The ones that go too far away from the sun to use solar energy, we can't use solar panels. So we put radioactive materials on them, and we actually use that heat to generate electricity. But here we have an entire protoplanet with radioactive materials, and there is plenty of them in the early times of the solar system. They were highly radioactive, and they're going to be changing to their stable form. They're going to be radioactively decaying, providing heat and energy to everything around them. So this is a strong contributor of heat. In fact, by the estimates of how much radioactive material we expect, there is a sufficient amount of radioactive heat being provided to the protoplanet to melt it, or at least melt it enough for differentiation to kick off. So this is our winner. This is the primary source of heat required to melt a protoplanet. So now that we have our molten protoplanet that's melted from the inside out, so it cooks it from the inside out and pretty much everywhere, now we can kick off the differentiation process. And kicking off the differentiation process actually speeds up the entire process by providing its own energy. It'll self-reinforce the process, but it is not the primary one. So once we have differentiation start, the dense stuff's going to start sinking down towards the center. The light stuff's going to start coming up for the top, to the top. So you're going to have these materials that are grinding against one another. And just like if you grind your hands together, rub them back and forth, you can feel them get hot from friction. As the dense stuff sinks and the light stuff floats, and you can actually try this at home, you'll feel your hands be warm. Then that's going to provide a little bit of an additional energy to speed up the differentiation process and keep it going. So that is our source of energy. And I want to spend some time talking about our winner right here. The primary source of energy required to melt a planet is radioactive decay. So we have to talk about radioactivity. And if we have to talk about radioactivity, we get to talk about one of my favorite scientists of all time. Probably does not get enough mention or airtime. Hopefully you've heard of Marie Curie. She was an absolutely extraordinary scientist. She coined the term radioactivity. She was the one that pioneered all of our understanding of how radioactive elements decay. So this is going back to ideas of how atoms behave at their fundamental nature. Absolutely astounding work. And it won her, her pioneering work on radioactivity actually won her a Nobel Prize in Physics in 1903, making her the first woman to receive the Nobel Prize in Physics. More so, I mean, she didn't just stop with radioactivity. She was a prolific and brilliant scientist. She kept on working and actually won a second Nobel Prize, the first woman to win 2 Nobel Prizes, and won her second Nobel Prize in chemistry. And this was not for her work on radioactivity. It was a follow-up. It was discovery of the elements radium and polonium, and then a lot of ways that we can use radium and polonium to develop things like medical technology that is saving lives still today. And winning a Nobel Prize in physics and chemistry makes her currently the only human that has ever lived that has won 2 Nobel Prizes in separate fields. So, a powerhouse of a researcher. Definitely deserves a little bit of attention and a little bit of credit. And we should also mention her family as well, probably the most prolific scientific family that's ever happened. So with her husband, Henry Becquerel, and then her daughters, the family has a total of 5 Nobel Prizes. So a pretty amazing scientific family. Now, I do want to point out, while they were discovering radioactivity, we didn't know what it was. We didn't know the dangers of it. So unfortunately, essentially every Curie died from cancer later in life due to radioactivity and being exposed to radiation. It's a sad story, so we should honor their contributions to humanity, and we do so in a variety of ways, and they have saved innumerable lives with all the technology that they've given by understanding radioactivity. So, what is radioactivity? So here we have a radioactive atom. You can imagine uranium-235, or uranium-238, plutonium, any, pick your favorite one. Carbon-14. Let's go with uranium-235. These are the ones that are most famous because they're used in nuclear weapons. So we have our radioactive atom. It's not happy with its nuclear makeup. It doesn't like the balance of protons and neutrons it has in its nucleus. So it's going to be unstable. It wants to change its nuclear makeup. So it will undergo a radioactive decay, as we call it. So it will shoot off a particle that will leave a nucleus. So it'll shoot off a nuclear particle, either a proton, a neutron, or a series of protons and neutrons. And it'll shoot off some energy as well. So a radioactive atom, a radioactive isotope, is going to be firing off particles of energy all the time. This is what makes it so dangerous, because that is some high energy stuff that can actually disrupt the molecular bonds in your DNA and other things. So a lot of energy is shed both as just light and as particles. And an element that does this, we say, is radioactive, and the process of it changing from an unstable, doesn't like its nuclear makeup, to a stable one, we call radioactivity, coined by Marie Curie. So we're going to have to review a little bit about atoms and what atoms are, how we define atoms, and we're going to introduce a new term, isotopes of atoms. So let's go ahead and hop right in. I want to give you an example of an isotope, and then we can generalize to what isotopes are overall. So whenever we talk about atoms, elements on the periodic table, the number of protons in the nucleus is what defines the element. You have 1 proton in your nucleus, you're hydrogen. You have 2 protons in your nucleus, you are helium. You have 6 protons in your nucleus, you are carbon. You have 26 protons in your nucleus, you are iron. So the number of protons defines what element you are. But protons are not the only particle in the nucleus. We also have neutrons. And the rules on the number of neutrons is a little bit more relaxed. So the number of protons that you have defines the element number. The number of neutrons you have defines what isotope of that element you are. So let's take the example of hydrogen. So normally, what we consider normal hydrogen, the kind that you have thought about every time you've thought about hydrogen, I'll imagine you do that all the time. You have one proton and no neutrons, and then you have an electron going on around it. Our normal form of hydrogen, what we usually just call hydrogen, but as an isotope, whenever we consider the number of protons and neutrons, this is actually called protium. Protium is the most common isotope of hydrogen. But we can play a little bit fast and loose with the number of neutrons, so we can add on an extra neutron. So now we have one proton and one neutron. One proton, so still hydrogen, but now we have an additional neutron. We have a different isotope of hydrogen. And this isotope of hydrogen is called deuterium. And we can play the game again. We could put two neutrons, one proton, and now we still have hydrogen, one proton, but we have two neutrons. So we have a different isotope of hydrogen called tritium. Tritium is radioactive. If you've heard of tritium, you've probably heard of it in relation to nuclear bomb tests. So now we can see by this example, the number of protons defines the element. The number of neutrons defines the isotope of that element, and not all isotopes are stable. Some of them don't like having as many neutrons to the number of protons they have, so they will become radioactive and they will try to change their nuclear makeup, their balance of protons and neutrons, to find some stable configuration where they're happy with the number of protons and neutrons they have in the nucleus. I do want to talk a little bit about how we label isotopes, since now we have to differentiate between the element and then the isotope of that element. It's good to have some standard way of communicating it. The formality of it is captured in isotope notation. So I'm going to refer to this generic notation, but I'm going to use carbon as an example. So the X right here and the isotope notation, that is just the chemical symbol for the element. So let's take carbon. Carbon, so we indicate the element carbon with the capital letter C. So I know I'm talking about carbon. The Z right here refers to the number of protons. Carbon has 6 protons, so we put a 6 right here. So Z equals 6 for carbon. And then A up here is the atomic mass. It's the total number of protons plus neutrons. So the stable form of carbon, the most common form of carbon, has 6 protons and 6 neutrons. So 6 plus 6 equals 12, so we put a 12 right here. And this is how we would write the isotope. Carbon-12 is how we usually say it. This is how you would formally write it. Now, notice that carbon and the 6 are redundant. All carbon atoms have 6 protons. So usually we'll not put this number down here, and we'll just put something like 12 carbon, carbon-12. And now we know what isotope. We know the number of protons and the number of neutrons that we're talking about for that isotope of carbon. All right, so now we can talk about stable versus unstable isotopes. Because if you start adding in extra nuclear particles, the atom is not necessarily going to be happy. This comes down to the other fundamental forces of nature, the nuclear weak force in particular. We will go into those details, but suffice it to say that if you put too many neutrons there, the nucleus isn't happy and it's unstable. It's going to change its nuclear makeup. The total number of neutrons and protons is going to change so that it can turn from being an unstable isotope to a stable isotope of a different element. So whenever you go through a radioactive decay, there are a number of ways. You can see the supplemental slides for different types of radioactive decay. But let's say one of the simple ways is going to take a proton and turn it into a neutron. So we could say have a proton that's in the nucleus. It's going to change into a neutron. A proton has a positive charge, so it has to balance it out with releasing a negative charge, because a positive and a negative equals a neutral. So in that case, the radioactive decay, that atom would shoot off an electron and a few other fundamental particles, and it would change one of its protons to a neutron, moving down on the periodic table. It would only have, if we were talking about carbon, instead of 6 protons, it would now have 5 protons. It can also shoot off a collection of protons and neutrons, usually in pairs of 2. So 2 protons and 2 neutrons will shoot off, also called a helium nucleus. And it'll shoot off that energetic particle called an alpha particle. So a number of ways that a atom can change itself from a stable to a stable isotope, or unstable isotope, to a stable isotope of a different element. And in the process, it sheds a bunch of energy. And that energy is going to be what's needed to melt a planet. So when a unstable isotope is going to undergo a radioactive decay, it really is going to be changing its nuclear makeup. It will turn into a different element. No, this is not alchemy, it is radioactivity. How do we actually start referring to a radioactive decay? So whatever radioactive isotope we start with, we call that the parent nuclide, or the parent isotope. It's going to radioactively decay into something stable that we'll call the daughter nuclide. So as it's shedding out those particles, shooting the radioactive shooting particles off in its radioactivity, dumping energy into everything around it, a parent is turning into a daughter, is how we say it. Now, this is a truly Gaussian random process. I know those are some mathematical terms, but it is a truly random process that follows what we call a Gaussian distribution, a bell curve-like distribution. And this means that we get to bring to bear all the power of mathematical statistics, which is great because now with a truly random process and a strong understanding of how math works and how statistics and probability works, this allows us to see that we can define a very, very characteristic time that will tell us how long it takes for you start with 100% parent radioactive material. How long will it take for it to go from 100% radioactive to 50% radioactive and 50% stable daughter? So how long will it take for half of the radioactive material to undergo a radioactive decay? And every radioactive isotope has its own characteristic time for half of it to decay from parent to daughter, and that time period is what we call half-life. No, not the video game, but the video game did take the name from this process. So half-life is the characteristic time for a radioactive isotope. How long will it take for half of that material to undergo a radioactive decay and turn into a stable daughter isotope? This is the most important part about radioactivity, perhaps, because it allows us to, one, do radioactive dating, which is a very, very powerful tool that we use in science. But it also gives us a way of actually tracking what's going on in a pretty stable way. So we can actually track the radioactivity. How radioactive an element is defined by its half-life. A radioactive material that quickly turns all of its radioactive stuff into half radioactive and half not radioactive, some that has a short half-life, is very radioactive. Don't touch that stuff. Don't even go near it. In fact, if I had a highly radioactive material sitting here in this room with me, I would die. So highly radioactive stuff has short half-lives. Subtly radioactive, low radioactive stuff, like thorium, which is out in our sidewalks and our streets, will cause a Geiger counter to go crazy, has a very long half-life, and it's not as radioactive. I want to give you a little bit of information, and I'm going to end this video by giving you a demonstration of how half-lives work. This is just sort of a start. So what I'm going to do is I'm coloring the green circles are the parent radioactive isotope, the unstable one, and they are going to decay via radioactivity to a daughter isotope. So let's start with 16 radioactive, say uranium-235. And at the start, we have all 16 of them are parent radioactive ones. Let's wait one half-life. So after one half-life, half of the radioactive particles will have decayed to their stable daughter. So now we would have 8 radioactive uranium particles, and we would have 8 daughter products. Eventually, it ends up as lead. So uranium, lead. Let's wait one more half-life. Well, we still have 8 radioactive particles, so over the next half-life, half of those will decay to daughter. So now we have 4 remaining radioactive particles and 12 stable daughter particles. Wait another half-life. Now we have 2 radioactive particles and 14 stable particles. Wait another half-life. Now we have 1 radioactive particle and we have the rest as daughter particles. So after one half-life, half of the radioactive stuff has turned to daughter. After another half-life, half of what was remaining. So here we have 50%, 25%, 12.5%, 6.25%, and so on and so forth for a number of half-lives. This gives us a very, very powerful tool. Because if we know how long the half-life is, then what we can do is we can actually go out and we can examine materials like meteorites or things that we find here on Earth, see how many radioactive parent particles they have to how many non-radioactive daughter particles that they have. So we can measure the ratio of radioactive parent isotope to non-radioactive daughter isotope. And that ratio will tell us how many half-lives have passed. So if it's 50% parent, 50% daughter, 1 half-life has passed. If it's 25% parent, 75% daughter, 2 half-lives, then 3 half-lives, 4 half-lives, so on and so forth. And what we can do is then we measure the ratio of parent to daughters, and we can backtrack all that to get the age when it would have been all parent. That gives us a way of telling how old that material is. That is how we do radioactive dating, which is a very, very powerful tool. We do this with meteorites with a whole host of different radioactive particles, and that's how we get the age of the solar system. Carbon-14, a unstable form of carbon, has a very short half-life, about 10,000 years or so. So very, very good for dating things, organic life in modern histories on timescales of tens of thousands to hundreds of thousands of years. If you want to use things like hafnium tungsten or lead or uranium or thorium with half-lives in billions of years, then you can date things like meteorites to determine the age of the solar system is 4.6 billion years old. Now, what I described to you is a pretty clean process. It assumes that you started with 100% parent and all daughter. Nature is not always that nice. There's always a mix. So if you had some daughter isotopes already there, how can you actually track what's going on? So that's where things become complicated. And that's why we're going to leverage multiple lines of dating that we can use. So we can trace all of those lines backwards in time and see where they all converge on a set date. So that's why we use multiple lines of radioactive isotope dating to come up with an age. Or there are certain scenarios where only parent material is let in, and I say a mineral will not accept daughter material. So it does start as 100% parent. And this is why, if you ever read about this, zircons, which only let in radioactive uranium, are great for using to do radioactive dating, because you start with 100% parent, and then it is as easy as it described in the previous slide. So I want to end by actually showing you a demonstration of all of this. I wrote a program that should demonstrate radioactive decay and half-lives. Hopefully you can now see my full screen. So here's my computer program. Don't worry about the details. I'm just going to run it. So here we have a whole bunch of green radioactive particles. Actually, it's 42 by 42. You can do the math in your head. Once this starts, every time step that it goes through, so it started now, it has every green radioactive particle has 0.5% chance to decay into a daughter stable blue particle. So we're at about 50% green, 50% blue. We've seen one half-life. We can wait exactly one more half-life, the same amount of time, and we'll have 25% green, 75% blue. We're not quite there yet, but you can see this process is continuing. It's a truly random process. It's happening everywhere. Now, what I want you to picture is every time one of these greens turns to a blue, it's shooting off energetic particles in every which direction, heating up all the material around it. So if we're looking at the interior of a protoplanet, we are melting all the material so we can kick off differentiation. So now we've gone through probably about 3 half-lives or so. We're not quite to the point where I want to start picking my favorite, which one I think I'm going to survive. So I'm going to take a sip of coffee. All right, so we're dwindling down. This process takes about a total of 2 minutes or so. There are a couple left. Let's see if I can pick my favorite. I think this one right here is going to be my last one. It's a truly random process. We'll find out if I'm right. Pick your favorite as well. Let's see if it survives. Every time green goes to blue, energy is released, heating up everything else around it. It was a truly random process. Oh, I am not a winner. I did not pick well. So let's go with this one. So now we're starting to see a little bit of the randomness will not play out as nicely. We have 4 particles, 3, wait in our half-lives, wait in our half-lives, down to 2. Did I pick correctly? As you can see, now that we're just waiting on 2 of them, every time they have the same probability of decaying, so now it's not as well controlled. It's a little bit harder to predict. Oh, I chose correct. And now we just got to wait for this last one to decay. And I can show you that this will demonstrate half-lives quite well. I can show you what's called a radioactive decay curve that my program will automatically generate for us. So if this one can just go ahead and decay, you can do a little green dot. I think with Zoom running and me doing a screen share, it actually makes my program run a little bit slower because the time step is dictated by how fast my processor is working. I believe this is what they call dead air. Ah, we're done. Okay. So my program pops out some plots. So what we're seeing here on the x-axis is time, and this is number of parent particles left. So this is tracing out the number of parent particles, so the number of radioactive particles over time. This is just a line that I'm putting so I know how many that I started with total. And you can see it decays pretty rapidly. Whenever it goes from, so right around 1600 to half that number. So right here, so this is 1 half-life. So 1 half-life has passed. Now I have 50% radioactive, 50% daughter. So 50% green, 50% blue, 2 half-lives, 3 half-lives, 4 half-lives, so on and so forth. And no, I did not evenly space these. My computer program picks, it just finds where it's half what it used to be each time. So you can see that this process really does work. So if I go out there and say I measure, I have this much parent radioactive material to this much daughter, that ratio, then I know 1, 2, 3, and about 3.5 half-lives have passed. I know a half-life is, say, 1,000,000 years. So 3.5 million years for it to get to that point on the curve. And you can do radioactive dating. So that's it for my lesson on radioactivity. And we have set the stage so we can actually melt a planet. We start video 2 by returning to differentiation and seeing how it plays out. Thank you for tuning in. I will see you in video 2.